Hello students, welcome to today's class. Yesterday, I have started the chapter Transistor Amplifiers. I am continuing that chapter. Transistor Amplifiers, where we started with the definition for amplifier, the definition for amplification, faithful amplification, and the role of selection of the cue point in the operation of the amplifier, and also how it affects when we are selecting the cue point near the cutoff region, saturation region, and middle of the cue point. And then I also discussed the different types of transistor based on different categories. Different types of transistor we have discussed in yesterday's class, and also we have seen the parameters wherein we have studied the voltage gain, current gain, power gain, the input and output impedance and bandwidth, and the lower and upper cutoff frequency we have discussed in yesterday's class. So now next I'll be moving to the next discussion, that is gain in decibels. Gain in decibel. Yesterday we have seen three types of gains while discussing the parameters of the transistor, wherein we have seen the voltage gain, the current gain, the power gain. Okay? But there we have observed that gain is the gain is basically the ratio of output quantity to input quantity. It may be voltage, current, or power. So when it is about the voltage gain, the numerator as well as the denominator is having the same quantity and the units are same, resulting into the gain to be a unitless quantity. So what we have observed there, that gain is unitless. It is not having any unit. That is because the definition is the ratio of the two similar quantities, resulting into no unit for gain. Okay, that's why gain is represented in bell. Gain is represented in bell. Okay, where bell is defined as common logarithm, that means log to the base 10. Common logarithm of power gain. Of what? Power gain. Okay. Normal, otherwise common logarithm of the power gain is bell. One more thing you need to observe here is that bell is a very large quantity. Okay, bell is a very large quantity. That's why we use decibel. Decibel to represent gain. Decibel to represent what? Gain. So, about the gain in decibels, we need to remember these things, that gain is first of all a unitless quantity. That's why we are representing the gain in terms of bell, and bell is defined as the common logarithm of the power gain. But bell is a large quantity. Bell is a very large quantity. So, in practice, we go with the unit decibel. So whenever we are going to represent the gain, we are going to represent in terms of decibel. Okay. Now, when we are representing the gain in terms of decibel, the gain which we have seen in yesterday's class is AV, that is voltage gain, AI, that is current gain, and AP, that is power gain. Now, these gains in terms of dB, how they are computed. Gain in terms of dB. So how the gain is computed in terms of dB? When you know the gain in terms of simply the ratio of output voltage to input voltage, we have a gain. How to calculate it in terms of dB? 20 log to the base 10 of AV is AV in terms of dB. Okay, 20 log to the base 10 of AI is current gain in terms of dB, and 10 log to the base 10 of AP, that is power gain in terms of dB, is represented by that formula, otherwise expression. Okay, so this is about the gain in terms of dB. Now I'll take a very small example for this. So there is a small problem in an amplifier. Voltage gain is, that is AV is given. AV is equal to 126.93. 126.93. Okay. And current gain is 100. AI is equal to 100. Okay. They are saying you find AP. They are saying you to find AP. That means the power gain and also all the gains in terms of dB. Okay. So they are asking you to find AV dB, AI dB, and AP dB. All these are asked to calculate. Okay. So now AV dB. First, we will just compute the value of AV because it is just the product of the two voltage and current gains. AV into AP. Sorry, AI. 126.93 into 100. 12693 is AP in normal representation. Now in terms of dB, AV, dB. AV in terms of dB, that is 20 log to the base 10 of 126.93. The log of 126.93 is 2.1034. 2.1034. Okay. Which is just when we are going to compute the value into 20, it is going to give you 42.017. 42.017 is AV in terms of dB. Okay, using this formula, we have computed the value of AV in terms of dB. Next is AI in terms of dB. Okay, AI in terms of dB. So what is the formula? 20 log to the base 10 of AI. And what is AI? It is 100 log to the base 10 of 100. And 100 log is what? Just 2. So this is going to give you 40 dB. AI in terms of dB. Next, what they are asking, AP in terms of dB. Okay. So they are giving the value of voltage gain, they are giving the value of current gain, they are telling you to find the normal power gain value and also all the gains in terms of dB. So normal power gain is just the product of the voltage gain and current gain. So this is the answer. AB in terms of dB, 20 log to the base 10 of the given value, that is 42.07 or 071. Coming to this, AIDB, 20 log to the base 10 of 100, 100 log of 100 is 2, so 20 into 2 is 40. Now 10 log to the base 10 of this 12693. So log of 12693 into 10 is going to give you what? 4.103. Log of 12693 is 4.103. So that is going to give you 41.03 dB. This is the value for power gain in terms of dB. Okay. So this is just the representation of gain in terms of dB. How we are going to convert a normal gain, that is the ratio of output quantity to input, that is when we are talking about the voltage gain, then it is the ratio of output voltage to input voltage of an amplifier. Current gain, ratio of output current to input current, ratio of output power to input power, which can be also computed as the voltage gain into current gain. Okay. So when they are giving the voltage gain in terms of dB, how it can be computed is 20 log to the base 10 of the given value. Log to the base 10 value into 20 is going to give you the value for AB dB. Okay. Now the AIDB, that is the current gain in terms of dB, is again computed with 20 log to the base 10 of AI. The value of AI is 100 and log of 100 is 2. So 20 into 2 is going to give us what? The value is 40. Now the AP is 20 log to the base 10 of this value. Okay, and this value is having 4.103, and that is going to give you a final answer of 41.03 dB for the power gain. Okay. So this is how the gain is represented in dB. Now we'll discuss why to represent the gain in terms of dB. Otherwise, how it is beneficial for us. Otherwise, how it is advantageous to represent the gain in terms of dB. This is what we are going to discuss now. Why gain is represented in decibels. In dB. Okay. So this is also a very oftenly used question in your final exams. Why to represent the gain in terms of dB. So here basically it is having three major points to use the unit for gain as dB. So what it is basically is, dB is normally a logarithmic unit, right? We are using logarithmic unit, that is dB here, and it is logarithmic in nature, and naturally the human ear response is also logarithmic. Okay, human ear, that means our ear that we listen from, okay, that is also having a natural logarithmic response in nature. Okay, so how it is means, when we are going to increase the loudspeaker sound by 100 times, okay, we are increasing the sound practically by rotating the knob, otherwise just by increasing the number by 100 times, okay, then the human ear can observe the sound to be doubled. Okay, log to the base 2 is log to the base 10, 100 is equal to 2. Okay, what we are actually doing, we are increasing the volume by 100 times. That means if the volume is at 1, I am making it 100. I am increasing it by 100 times. When it is increased by 100 times, we can observe, our human ear can observe it to be doubled. Okay, so this is the natural response of the human ear, and that is logarithmic. And gain we are representing in what? Logarithmic unit. So what happens here? The logarithmic unit is what we can say matching with the human ear response. That means it tallies with that. That's why it is preferred to represent the gain in terms of dB, because it is naturally going with the response of the human ear. That is one reason. Okay. The other reason is gain in dB of multiple stages can be added. Can be added, otherwise is added. Okay? Can be is added. What does this mean? We have discussed little about the single stage and multi-stage amplifiers, where one stage is not able to produce the required sound, then we are going to use multiple stages. So what happens here when we are going to compute the final gain? When it is normal unit for gain, then each stage gain is taken and it is multiplied. And when we are multiplying, what happens? The computation naturally becomes quite difficult. Okay, but when it is about the representation in terms of dB, decibels, then each stage gain can be simply added together. That means if we are using two-stage amplifier, first one is producing a gain of 2 and the second one is producing a gain of 3, then it will be simply 5. Okay, just adding them. Okay, so this is the other example. The third example, second advantage. The third advantage is that in dB scale, we can easily represent very small value of gain as well as a very large value of gain. Okay, that I am giving an example now. Log to the base 10 of 100,000. That means the log to the base 10 of this number, that is 1 followed by 5 zeros, is just 5. Okay, in terms of dB. Okay, 5 in terms of dB, and in terms of power gain, if we are going to represent it, that is 80 dB, then it will be just what? 50. Okay, just 50. 10 of 5, 10 of log to the base 10 of this number 1 000 is 5, and into 10 is just 50. Okay, and log to the base 10 of 0.00001 is minus 5 dB. Okay, so it will just minus 50 dB. So representing the gain in terms of normal representation takes a very large number for the representation. It is also taking a very large number for representation, whereas here it can be simply represented by 50 and minus 50. Okay, this is the third example. Advantage. So, why we represent gain in terms of decibel? Gain in decibel goes with means it tallies with the response of human ear. Human ear. Gain in decibel goes with the response of human ear. Okay. That's why it is suitable to represent gain in dB. Okay, gain in decibels, when we are representing the gain in decibels, it goes with the response of the human ear. That's why it's suitable to represent the gain in terms of decibels. Okay. Next, gain multiple stages amplifier is just added to get total gain. Okay, so total gain of a multi-stage amplifier when represented in terms of dB is just the addition of each stage. Next, representation of very small or very large gain in terms of dB is easier. Okay, so these are the important points that tells you why to represent the gain in terms of dB. Okay, so that is the responses. The both are logarithmic in nature. The human your response is also logarithmic, and the gain in terms of dB is also logarithmic. So both the response of the human ear and gain in terms of dB are suitable. Otherwise, they tally with each other. That's why it is better to represent gain in terms of dB. And a multi-stage amplifier, if it is there, and if you want to get the final stage, otherwise the total gain produced by the system, that is how much each stage is producing the gain, we have to compute the total gain. Then in terms of dB, if the gain is represented, then we have to just add all the individual stage gains to get the final gain. Okay. Whereas in normal representation, it will be the product. That means we have to multiply the gain of each stage. Then representation of very small or very large gain. Okay, I have taken the example also where locally base 10 of 1 0000 is 5 and 0.00001 is -5. So very small value as well as very large value can be easily represented in terms of dB. That's why we normally represent the gain in terms of dB for amplifiers. This is about the decibel. Now I am moving with the single stage amplifier. Single stage amplifier. In the single stage amplifiers, we will be studying three amplifiers, that is common base transistor amplifier, common emitter transistor amplifier, and common collector transistor amplifier. Each amplifier in detail we will be studying with the configuration as common base, common emitter, and common collector, which will be having a single stage. Okay. So what does that mean now? What is the meaning of single stage amplifier? Single stage amplifier. So a circuit, otherwise an electronic circuit with only one transistor and associated circuitry. Associated circuitry means whatever is required for its biasing and a required number of resistors. Okay. So total unit of amplifier having one transistor and associated circuit. Associated circuitry. A circuit with only one transistor associated circuitry that can increase strength of an input signal is called single stage amplifier. Okay, you can also define it as a circuitry that increases the strength of an input signal with only one transistor and associated circuitry is called single stage amplifier, or a circuit with only one transistor and associated circuitry that can increase strength of an input signal is called single stage amplifier. Okay. Of course, without varying the frequency or any change in the wave shape. Okay. So this is the definition for single stage amplifier. As I have told you, in the single stage amplifiers, you will be studying three amplifiers, that is CB, CC, and CE. Common base, common collector, and common emitter. Now I am taking the common base. The common base transistor amplifier with circuit and detailed explanation along with its characteristics. Okay. So for that I am drawing the circuit now. Common base, this is the transistor. This is base, collector, emitter, base and collector. This is RE because it is connected to the emitter terminal. Okay. The input, the in. Okay. Here there is the out. Okay, that is nothing but the voltage across the collector and base. That is VCB. Okay. Another voltage required for the biasing purpose here. Positive and negative. This is termed as VCC. This is VEE. Okay, and that is the transistor. Right? This is termed as RC. This is C2 and this is C1. This capacitor C2 and C1 are just for blocking the DC and allowing only the AC. That is, those are called as the coupling capacitors. Here, this VEE, as we know, this is what type of voltage it is. Here, it is N. This is P and this is N. Okay? So this particular voltage VEE with negative terminal is going to forward bias the what? The EB junction. Okay. Whereas with N, this is going to reverse bias the N is connected to positive terminal of this battery. So this particular junction will be reverse bias. Okay. So this is the CB transistor amplifier. Okay. We are also representing a voltage here, that is voltage VEB. The voltage across the emitter to base terminal is called as the VEB. That is the what we can say reverse voltage applied to the junction. Right. So this is the input where you are going to get the output at this part, and it will be a amplified version of the input, okay, which is having a greater amplitude. Okay, so this is about the CB, that means the common base transistor amplifier. Now I am going to explain you the operation. What happens here? The input is applied across the emitter and base terminal. Across the emitter and base terminal, input signal PN is applied, whereas the output is taken across the collector and base terminal, and the output voltage is represented by VCB, this voltage. Okay, and this is V is the input voltage. Okay. So what happens is when you are going to apply the input here, right? As the input is increasing, that means during the positive cycle. During the positive cycle. Positive cycle means this portion. This is negative cycle. Okay. During the positive cycle of input voltage, Vin, what happens? as the cycle is increasing, that means as it is taking the higher values like this positive cycle. Okay, the reverse bias voltage applied here is VEB. Okay, and this VEB is given by VEB is equal to VIN minus VEE. Okay, as VE is a positive value now, right? It is a positive cycle, so it is a positive value, and this is the reverse. Sorry, it is a negative value, right? Okay, and it is forward biasing the signal. As the input signal is positive and this signal is negative, the effect of the positive cycle is such that it is going to reduce the net value of VEB. That means what happens? The reverse bias voltage VEB decreases. The voltage applied to this particular input terminal, that means the voltage across the emitter to base VEB, the net effect is such that it is going to decrease. So total value of this VEB is going to come down. Okay, VEB value comes down. So as the value of VEB is decreasing, definitely the emitter current will decrease. Okay, here we are going to show the emitter current. Okay, emitter current will decrease. Here we are going to show the IC. Okay. So as the emitter current is decreasing, what happens? As a result, the base current also decreases and overall the collector current decreases. So what is happening here? IE decreases, IB decreases, and also IC decreases. Okay. So totally what is happening here? Because of the decrease in the IE, IC is decreasing. And IC is given by IC is equal to alpha times of IE. So as IE itself is decreasing, so what happens to the overall value of IC? It is also going to decrease. And how this final value VCB is given? VCB is equal to, see here the total voltage is VCC. So VCC is equal to ICRC plus VCB. So VCB is equal to VCC minus ICRC. VCC minus ICRC. So what is happening? Basically IC is decreasing. Okay, and VCB is total VCC minus ICRC. When IC is decreasing, so what happens? The value is increasing because the value that is getting subtracted is reducing. So overall effect will be increase in this VCB. Okay. So this VCB, that means the output increasing. Output keeps on increasing with the increase in the positive cycle. That's why it will produce a amplified. It is going to produce a amplified positive cycle at the output. Okay. So it will produce what? Amplified version of the positive cycle at the output. Okay. So this is about how it is going to operate. I am going to repeat the explanation again. Input signal during the positive half cycle. Input signal during the positive half cycle, the overall biasing voltage, that is the forward bias voltage for this particular junction, is given by VEB, and that VEB, how it is related to V is VE minus VE. As it is increasing, VE is increasing means what happens? Overall, the value of VEB is going to decrease. The net effect is that during the positive half cycle, the net effect on the VEB is such that it is going to decrease. When it is going to decrease, what happens? As the applied voltage itself is decreasing, so what will be the effect on the emitter current? Is that emitter current will decrease. Emitter current is decreasing, so base current will decrease. As a result, collector current also decreases. Collector current decreases, and the collector current is related with the alpha IE. Okay, alpha IE. So what happens? Collector current decreases, and the final current, the final output voltage is depending on the collector current. So VCB is equal to VCC minus ICRC. As this is decreasing, so what happens? Overall VCB is increasing. So as the just we relate the input and output waves, then as the input wave is increasing, the output wave is also increasing, but in a amplified form. So it will, for the positive half cycle of the input voltage Vin, we will get a positive half cycle of the amplified version of the input signal. Okay. So what happens during the negative half cycle? I am just going to explain now. Exactly the reverse process happens for the negative half cycle. When we are applying the negative half cycle, it is going to what? It will increase the overall effect of the VEB is that it is going to increase. VEB will be increase. The net effect on the voltage, the biasing voltage is such that the VEB is going to what now? Increase. VEB will increase. With increase in the VEB, what happens? IE also increases. IE increases, IB increases, also IC increases. Why IC increases? Because of this relation between the IC and IE. IE is increasing, so alpha times of IE, IC will also increase. Okay, and just to see here, the value of the term that is being deducted from the VCC is increased. So what happens on the overall effect of the VCB is that VCB is going to now decrease. Okay, VCB is going to decrease, producing a negative cycle for the incoming negative cycle of the input, but a amplified form of that will be appearing at the output. Okay, so this is about the CB transistor amplifier. Okay. So I'm just going to write it point wise, one by one, the entire thing now. During positive cycle, half cycle of input AC signal. Input AC signal. Okay, so what happens here? I'm just explaining the working. So what happens? Net voltage or net bias voltage VEB decreases. Okay. I'm writing it point wise so that you can easily understand it. So what happens? Net voltage VEB decreases. Okay. As VEB decrease, IE, ammeter current, decrease, IC also decrease, as IC is equal to alpha times of IE. Okay, IC has decreased now. So what happens? The output voltage between collector to base terminal, collector and base terminal, VCB is given by what? VCB is equal to VCC minus IC RC. Okay, VCC minus IC RC. Therefore, VCB increases by producing a positive half cycle with amplification, the amplified version of that, with amplification. Okay, with amplification, right? So this is what is going to happen in the CB transistor amplifier. And about the negative half cycle, we can just write that the net voltage VEB increases, as a result IE increases, and IC also increases. As IC is increasing, what is happening here? VCB is going to decrease because of this relation between the VCB and IC. So VCB decreases, that produces a negative half cycle with a amplified version. Okay, so this is about the transistor, CB transistor amplifier, where we are studying the CB amplifier in the single stage amplifiers, where I have told you that you will be studying CB, CE and CC amplifier, where we are studying the CB amplifier, transistor amplifier now, where we have seen the circuit and its entire operation of the CB amplifier here. Okay. Now the characteristics of CB transistor amplifier. CB transistor amplifier characteristics. Okay. First, it has very low input impedance. Very low input impedance. The second point, it has very high input impedance. Sorry, output impedance. Next, it has very low current gain. Current gain is very less. Current gain, and that is represented by alpha is less than 1. Alpha is less than 1. Then it has very high voltage gain. Voltage gain is high, current gain is low. Very high voltage gain. Okay. Next, it has moderate, that means medium. Moderate power gain. Moderate power gain. Okay. And finally, there is no phase reversal. There is no phase reversal. Reversal from input to output. So what does this mean? Yesterday in the transistor parameters we have studied all these parameters, almost all these parameters we have discussed. That is the input impedance. What is the input impedance? The overall opposition offered by the input part, otherwise the input portion of the amplifier is called input impedance. So the input portion of the amplifier, a CB amplifier, is going to offer a very low input impedance. Okay. And it has a very high output impedance. Output impedance means the total opposition offered by the output portion of the transistor amplifier. See, very low input impedance is offered because the input side, that means the what we can say, EV junction is forward biased. Forward biased, it will easily allow the signal to enter inside. So very low input impedance is offered. Whereas the CB junction, that means the output portion of the transistor, was reverse biased. That's why it is going to offer a very high output impedance. So very low input impedance and very high output impedance. It is having very low current gain, that means alpha is less than 1. Okay. It has very high voltage gain. Okay, voltage gain, current gain and power gain we have discussed in the yesterday's class in the parameters, that ratio of output current to input current, ratio of output voltage to input voltage, and ratio of output power to input power are current, voltage and power gain respectively. So here it is having very low current gain, alpha is less than 1, very high voltage gain and a moderate power gain. There is no phase reversal from input to output. That means input signal and output signal are in phase. Both are having. That means whenever there appears the positive cycle of the input, there also appears the positive cycle of the output. That means both are in phase. There is no phase reversal. Otherwise, there is no any value of phase. What we can say, disturbance. Otherwise, the phase discrimination between the input and output wave. Okay. Both are in phase. That means whenever positive signal is having the input signal is having positive cycle, output will also have positive cycle. Both are in phase. There is no any degree angle of phase reversal between the input to output. Okay. So these are the characteristics of CB transistor amplifier. The CB transistor amplifier operation also we have studied. The entire operation is written here. Okay. So what all we have studied in today's class is about the decibel and how the gain is represented in terms of decibel. That is the 20 log to the base 10 AV for AV in dB, AI in dB, 20 log to the base 10 of AI, AP in dB, that means the power gain in terms of dB, 10 log to the base 10 of the normal power gain we have to compute. Then why to use the decibel unit, otherwise why it is preferred to represent the gain in terms of decibel. I have given 3 reasons there. That it goes with the natural, the scale of representing the gain in terms of dB. That means using the logarithm is going with, otherwise is suitable for the human ear response. That means both are logarithmic parameters, right? That's why it is one of the reason to use the gain in terms of decibels. Then when we are using multiple stage amplifiers, when we want to compute the total gain produced by any system, individual gain is just added to produce the final gain when the gain is represented in terms of dB. Whereas in the normal representation, the total gain will be the product of individual gains of the stages, right? This is the second advantage. The third advantage is that largest to largest value, very large value and a very small value, where there I have taken the example for log to the base 10 of 1000000, that is 5, and 0.000001 is -5. Okay, so representation becomes easy in terms of small numbers. Okay, That is the third advantage. Okay, and then we moved to the CB amplifier, where we have seen the working in the positive and during the negative cycle also, and we have seen the characteristics of CB amplifier. This is all about today's class, students. Thank you.